Network covalent atomic solids. We're going to look at carbon and silicates. So elemental carbon exists in different forms. Different forms of an element are called allotropes. So in graphite, we've got carbon atoms that are covalently bonded to each other in flat sheets of interconnected hexagonal rings. So here's an illustration of that. We have a two-dimensional sheet of carbon atoms, and it contains carbon atoms bonded in little hexagons, and those hexagons are interconnected. So covalent bonds holding the atoms together. This is a network covalent atomic solid. Between this layer and the next layer, what holds them together is just dispersion forces. The only intermolecular force possible for atoms is dispersion forces. These are all carbon atoms. We can't have any polar bonds of any sort. So we've got dispersion forces holding the layers together. Dispersion forces are weak, very weak compared to the covalent bonds. So as a result, these layers can slide past each other fairly easily, and that makes graphite slippery. Makes it useful as a lubricant, makes it useful as a pencil lead. Your pencil lead does not contain any lead. It's graphite. And as you write with it, the graphite shears off and leaves bits of it behind, and there's your pencil marks. Graphite's a good electrical conductor along the, in the plane of the sheets. It doesn't conduct well across this way. But it's got an extended delocalized pi network, and so it can conduct electricity that way. Here's a picture of some naturally occurring graphite. And if you hit that with a hammer, it's going to shear in planes because it'll break between the layers. Graphite has a density of 2.2 grams per cubic centimeter. If you put a lot of pressure and heat on that, and we're talking a lot of pressure, like 50,000 atmospheres, it's crazy, and 1,600 degrees Celsius, you can cause the atoms in graphite to rearrange and form diamonds. Diamonds are more dense. They have a density of 3.5 grams per cubic centimeter. So the diamond structure, again, we see the hexagons of carbon, but now the covalent bonds are extending in 3 dimensions instead of just 2 dimensions. That diamond unit cell is similar to the zinc blend cell that we just looked at, where here we had face-centered cubic, and then we had zinc ions in the tetrahedral holes. For the diamond structure, you've got that face-centered cubic, but in the tetrahedral holes are also carbon atoms. So they're just all carbon atoms. So what we've got here is in each of those tetrahedral holes, you've got a carbon that's bonded to 4 other carbon atoms. And if we remember from our study of bonding theories, we know that carbon likes to make 4 bonds, and it'll take on a tetrahedral geometry. And so carbon's pretty happy in this diamond structure. Because it has covalent bonds extending in all directions, it has a very high melting point, about 3,800 degrees Celsius. It's very hard because in order to break a diamond, you have to break a whole bunch of covalent bonds. It's also an excellent heat conductor, but it doesn't conduct electricity. Because it's a good heat conductor and it's very hard, it's useful for abrasives and cutting tools. When you've got a cutting tool, it's often used moving at high speed. Think of a circular saw blade. It's moving, there's a lot of friction, it gets hot. You want something that's not going to melt or burn, and you'd like it to be able to conduct the heat away so that it doesn't get even hotter. In the 1980s, they discovered a new form of carbon by aiming a powerful laser at a carbon surface. The way that things get discovered in science often involves chance and stupid ideas, right? We all have these ideas, I think, of, oh, I wonder what would happen if I did this. The difference with scientists is they have enough knowledge generally that they could actually carry it out and usually do it without causing damage or harm to people or surroundings, at least not very much, right? So, I mean, who thinks of, well, what if I shine this really powerful laser at this carbon? I wonder what's going to happen, right? Who does that? Well, these guys did it. And what they discovered was a molecule like this. It's 60 carbon atoms, and they're covalently bonded together, but this is not diamond. This is making a sphere. It's hollow in the center. It's a ball. And it's got 6-membered rings and 5-membered rings interconnected, and it's very similar to a geodesic dome. And so it was named after Buckminster Fuller, who did a lot of stuff with geodesic domes. It's called Buckminster Fullerene. It's a soccer ball-shaped cluster of 60 carbon atoms. Then they, studied that one, and then they found out they could make others with different numbers of carbon atoms. So you can make them from about 36 to over 100 carbon atoms. As a class, these are called Fullerenes, and their nickname is buckyballs. What's the point of it? Well, a lot of times there really is no point when it starts out. People enjoy trying new things, making new stuff, and then you figure out what it might be useful for afterwards. Sometimes people set out to do one thing and accidentally do something else. That happens as well.
My question is going to be about their practical applications.
Mm-hmm.
Do you have any of them yet?
Well, let's go on to this slide, which is related to the buckyballs. So this idea of these interconnected hexagons, right? They can make nanotubes, which are long carbon structures consisting of these interconnected C6 rings. Nanotubes do have some practical applications. They look a lot like a roll of chicken wire. You can have a single-walled nanotube. You can have multi-walled nanotubes. So here these tubes are like nested inside of each other. Nanotubes are really strong, 100 times stronger than steel, and only 1/16 is dense. And so they're very, very, you've got a lightweight and very strong. So that's cool. So they are used in applications such as reinforcing golf clubs and bicycle frames. Graphite golf club. What's the graphite? Is it the slippery stuff in your pencil? No, it's this sort of graphite, formed into nanotubes. You can also have nanoribbons. This is the graphene sheet that we talked about earlier. You can take bundles of these nanotubes and make really tiny wires, much tinier than you could get from using metal wires. So there's lots of different applications, and of course there's people looking for more all the time.
And it started with the fullerene?
I'm not sure if it started with the fullerene or not. Probably. Any other questions? One of the reasons I'm actually going over this instead of saying, "Oh, just read it in your book," I hope to give you a grasp of how chemistry is very much involved in the everyday materials and in developing new materials. And everything is chemistry, really. It's made up of chemicals, atoms. Atoms make up everything. That's why you should never trust an atom, because they make up everything. Mm-hmm. Okay, so another network covalent atomic solid, silicates. You look at silicate, and silicates are extended arrays of silicon and oxygen. They're the most common network covalent atomic solids on the Earth. 90% of the Earth's crust is made up of silicates. Think sand, right? How much sand is there at the ocean? Lots of sand. Sand is composed of silicates. Silica is a silicate. It has a formula unit of SiO2. And you look at the formula unit and you think molecule. I think molecule, SiO2, that's a molecule, right? How is this a network covalent atomic solid? It's an atomic solid because it's atoms connected to each other with covalent bonds. Now granted, they are different types of atoms, but there are no discrete molecules in these compounds. So silicates take on shapes like this, where it's just an ongoing array, just essentially it's one giant molecule. So we've got these little tetrahedra that are connected. So you've got a silicon atom, and it is chemically bonded, covalently bonded to 4 oxygens. So here we have that illustrated. And if you look at this, is that a good Lewis structure?
Isn't the SI missing?
The oxygens are missing an electron, right? They don't have an octet. So what they do to make up for that, so this oxygen is going to be bonded to a silicon atom. The silicon atom is bonded to other oxygens. Okay, so this oxygen actually is happy because it's bonded to 2 silicons.
But is the silicon empty? Or does that have a formal charge of it?
The silicon has a formal charge of 0. Silicon is in group 4, just like carbon.
Sulfur. Oh my gosh.
Yeah, not sulfur.
Oh god.
Yeah, it's okay. And so it just goes on and on and on. So this one is bonded to another silicon. And it just keeps going. Now, obviously, somebody at the edge has to be unhappy, but we don't have to go all the way to the edge. So it just goes on and on and on. Quartz is one form of silica. This is the quartz structure. You can have silica in other crystalline forms.